Welcome to G Fun Facts Online, where we dive deep into the fascinating world of science. Today, we're exploring a field that combines the meticulous work of a detective with the profound science of our planet's most vital resource. Imagine a crime scene that's constantly moving, erasing its own tracks and holding its secrets in the silent depths. That crime scene is our waterways, and the detectives are forensic hydrologists. They read the stories told by rivers, lakes, and groundwater to unmask silent polluters and find those tragically lost. This isn't just about studying water, it's about making water talk, revealing truths that would otherwise remain submerged forever. Forensic hydrology is, at its core, the application of water science to answer legal questions. It's about piecing together the past, whether it's a mysterious chemical spill, a catastrophic flood, or the heartbreaking journey of a drowning victim. These scientists investigate everything from why a basement flooded to who contaminated a town's drinking water, using the principles of water's movement to unravel complex mysteries. At the heart of all this is the hydrologic cycle, the endless journey of water from evaporation to precipitation and runoff. For a forensic hydrologist, this cycle isn't just a diagram in a textbook. It's the forensic playground. It's the highway system that transports clues. The way water flows over land, seeps into the ground, and travels through rivers is governed by topography, geology, and human changes like dams and cities. Investigators analyze historical weather data, topographical maps, and even old aerial photos to reconstruct the exact conditions at the time of an incident. They build a complete picture of the crime scene, whether it's a contaminated aquifer hidden deep underground or a raging river that has become a tragedy stage. One of the most critical roles for a forensic hydrologist is tracking invisible culprits, pollutants. When a waterway is contaminated, the damage to public health and the ecosystem can be immense. But how do you prove who did it? Especially when a river has multiple industrial sites along its banks. This is where a sophisticated scientific toolkit comes into play. The first major tool is called chemical fingerprinting. Just like a person's fingerprint is unique, so is the chemical composition of a pollutant. Imagine a factory leaks a specific blend of solvents into a river. By taking water samples downstream, scientists can analyze that chemical cocktail. They look for specific compounds and their relative concentrations. If that unique chemical signature matches the chemicals used at the upstream factory, they have a direct link. It's like matching a suspect's handwriting on a note left at the scene. For example, finding a specific type of pesticide might point directly to an agricultural operation, while a unique mix of heavy metals could be traced back to a single manufacturing plant. This technique turns the water itself into the key witness. But what if the source is more subtle, or you need to know when the pollution happened? That's where isotope analysis comes in. Isotopes are slightly different versions of the same element. Think of them as atoms with a little extra weight. The ratios of different isotopes of hydrogen and oxygen in a water molecule can tell a hydrologist its life story. Water from recent rainfall has a different isotopic signature than water from a leaking, decades-old sewer pipe or from a deep underground aquifer. By analyzing these isotopes, investigators can determine the origin of the contaminating water. They can even date groundwater, estimating how long it's been since that water was last in contact with the atmosphere. This is crucial for establishing a timeline. Did the pollution event happen last week, or has it been slowly seeping into the ground for the last 30 years? Isotope analysis helps answer that question. To truly understand how a pollutant moves, hydrologists use hydraulic modeling. Think of this as creating a video game or a digital twin of a river system. These are powerful computer programs that simulate the flow of water. By inputting data on the river's shape, its flow rate, and the properties of the pollutant, the model can predict the contaminant's path and concentration over time. This is invaluable for both looking into the past and predicting the future. For a past event, a model can reconstruct how a chemical spill would have spread, showing exactly which areas were affected. For a future threat, like an oil spill, models can predict the plume's trajectory, helping responders decide where to place containment booms to minimize damage. It's like having a crystal ball for water flow, allowing for smarter, more effective cleanup strategies. And now we're entering the realm of science fiction with a groundbreaking new technique, using DNA as a tracer. No, not DNA from a person, but synthetic man-made DNA particles. Scientists can tag water with these unique DNA markers and then track their movement with incredible precision. Imagine releasing millions of microscopic, trackable messengers into an underground water system. By sampling the water at different points, they can map out complex, hidden flow paths and transport times with a level of detail that was previously impossible. This DNA water labeling is a new frontier that promises to revolutionize our ability to track pollutants and understand the secret lives of our groundwater systems. Tragically, the work of a forensic hydrologist isn't always about pollution. Waterways can become the final resting place for missing persons. In these heartbreaking cases, science can offer a path to closure for grieving families. The primary tool used here is drift analysis. This is the science of predicting where a body might be found in a river or lake. It's far more complex than just calculating how fast the water is moving. A forensic hydrologist must consider a huge number of variables: the current, the water temperature, the wind speed, and the physical characteristics of the individual. The movement is complicated by the grim process of decomposition. As a body decomposes in water, its buoyancy changes. It might sink initially, then resurface as gases build up, and potentially sink again later. The rate of this process is heavily dependent on water temperature. Decomposition is much faster in warm water. Wind is another huge factor, as it can push a floating object across the surface, independent of the main current. By inputting all these variables into specialized computer models, investigators can create a probability map. This map doesn't show one exact point, but it highlights the areas where the victim is most likely to be. This allows search and rescue teams to focus their efforts, using their time and resources much more effectively. And these days, those search teams have incredible technology on their side. Remotely operated vehicles, or ROVs, which are essentially underwater drones, have revolutionized these searches. Equipped with high-resolution sonar that can see through murky water and powerful cameras, these ROVs can scan vast areas of a riverbed or lake floor. They can be programmed to follow a specific search pattern based on the drift analysis models, sending back data in real time. This technology allows searchers to cover more ground, more safely and more effectively than human divers ever could, and has been instrumental in locating victims in even the most challenging underwater environments. To see how this all works in the real world, let's look at a couple of cases. In one instance, a river suffered a major fish kill. Thousands of fish suddenly died, signaling a massive environmental disaster. A team of forensic hydrologists was called in. They started by taking water samples and samples from the dead fish. Using chemical fingerprinting, they identified a specific cocktail of industrial chemicals. This chemical signature was a perfect match for the waste products of a manufacturing plant located several miles upstream. But to prove it in court, they needed to show causation. Using hydraulic modeling, they recreated the river's flow conditions on the day of the spill. The model clearly showed how a discharge from the factory's location would travel downstream, reaching the area of the fish kill in the exact time frame it occurred. This combination of chemical and digital evidence was undeniable, and the company was held accountable for the damage. In another, more somber case, a kayaker went missing on a large, fast-flowing river. The search area was enormous and dangerous. Forensic hydrologists were brought in to help. They analyzed the river's powerful currents, the water temperature, and the wind patterns from the day the kayaker disappeared. They ran multiple drift analysis models, which narrowed the vast search area down to a few high-probability zones. A search boat equipped with an ROV and sonar was deployed to these specific areas. Within hours of searching the targeted zone, the sonar picked up an anomaly on the riverbed. The ROV was sent down to investigate, and tragically, it confirmed the location of the victim. While a sad outcome, the science provided a swift and certain answer, bringing closure to the family. The findings from forensic hydrology have major legal power. This work provides the hard, scientific evidence needed to take polluters to court and enforce environmental laws like the Clean Water Act. In a courtroom, a forensic hydrologist acts as an expert witness. Their job is to translate complex scientific data into a clear, understandable story for a judge and jury. Their testimony can be the deciding factor in cases of property damage, for instance, proving that a new housing development illegally altered water flow and caused a neighbor's property to flood. Their work also shapes the very regulations designed to protect our water, identifying pollution sources and pathways so that we can create smarter, more effective policies. So what does the future hold for this incredible field? As our world changes, the need for forensic hydrologists is only going to grow. Climate change is bringing more frequent and intense weather events, meaning more floods, more erosion, and new challenges for managing our water resources. Forensic hydrologists will be on the front lines of understanding and mitigating these impacts, and their tools are getting better every day. The use of remote sensing technology, like satellite imagery and LiDAR, which uses lasers to create detailed 3D maps of the landscape, will allow for even more accurate hydraulic models. The continued development of DNA tracers and other advanced analytical techniques will give them unprecedented power to track pollutants and understand their journey through the environment. In the end, forensic hydrology is a dynamic and vital field that sits at the intersection of science, law, and environmental justice. By giving a voice to our planet's most precious resource, these scientists ensure that the silent witness of water can tell its story. Whether they are uncovering an environmental crime or bringing a lost loved one home, forensic hydrologists work to right wrongs, provide closure, and protect our waterways for generations to come.